So the reason we care about this relationship is that getting a standard state free energy change for a reaction is difficult to do, but getting equilibrium constant from different concentrations is easier to do experimentally and then get delta G off of that. Anyone know any ways to get KEQ experimentally? It's like a technique you could use. Just guess.
Periodic table and a scale.
What? A periodic table and a scale?
Yeah, like more mass.
So that's related to it. Yep, okay. There's a lot of ways. The most popular ways you could use sort of like NMR spec and look at a chemical shift. A really popular one is something based on light spectroscopy, right? So these things have a different color, so they're absorbing light differently, or they're transmitting light differently, and so as it reacts, it's going from clear to color, or color to clear, and as that changes, you capture it. So yeah, fluorescence or absorbance. Light specs like number 1, NMR shifts would be number 2, and we talk about doing it with electrodes in chapter 11. You could also use calorimetry. You could also just do it with a computer model. Calorimetry is always the safe answer, right? Always a solid guess. Solves everything in this class. All right, so this goes through what we've just done, okay? It puts the change in free energy in terms of all of the chemical potentials. It talks about how the signs change for the reaction progress variable depending on whether you're forming, whether you're consuming or making your product or reactant. It sets everything equal to 0, okay? So the reactants and products are balanced, okay? They're not at equal concentrations necessarily, but the amounts are balanced. The changes in concentrations are not happening. Okay. This goes through all the math again, so you can watch it on here if you want to click through it. There they are. Equilibrium constant provides a way to determine the concentrations and the extent of a reaction at equilibrium. It's measurable and it's unitless. So here's an example of, say, molecular bromine. It's sort of a reddish-brown color, and as it reacts with formic acid, it turns colorless. And so what you can do here, essentially the change in concentration of your reactant is proportional to the change in absorbance that you're going to get. And so you can continually take absorbance measurements with a spectrophotometer, and as you see the change in absorbance drop off, you know that you have a relationship to the concentration change. Is one example.